Hello friends, once again I am here with a new topic or new point for the discussion. Before starting with the actual topic or actual point, let me write one structure by using a line formula, and the structure is like this. And this is the structure of butane. We know that it is having a molecular formula C4H10. If I put one double bond in this butane, then the structure become like this, and it gets converted into a butene, and the molecular formula is a C4H8. Once again, if I put another double bond in the butene, then this butene converted into a butadiene, and the molecular formula is C4H6. Here the word diene came, and this diene is nothing but two double bonds. Therefore, in this lecture, we will discuss aliphatic hydrocarbon with two double bond, and these compounds are generally called as a alkadies. So the point of discussion is alkadine. If you look at the structure of butane, butene, and butadiene, and the molecular formula of these compounds, then there is a decrease in number of hydrogens. Therefore, from the molecular formula of the butadiene, we can generalize this molecular formula like this: CnH2n minus 2. Therefore, a cyclic, what I'm saying, a cyclic alkadine, they have a molecular formula CnH2n minus 2. A cyclic diene, they may have a different molecular formula, but in this lecture, as we are going to discuss a cyclic alkadies, then this molecular formula is important one. Now, these alkadies, they can be named according to the IUPAC nomenclature, and in IUPAC nomenclature, longest carbon chain is chosen as a parent hydrocarbon. So we will take the example. Here I will write a carbon CH2 double bond CH, single bond CH, double bond CH2. Then next example I will write somewhat longer chain. Here CH3, C, CH3, double bond CH, single bond CH. Again it is having CH3, then CH double bond CH2. What we have studied, the longest carbon chain with a two double bond is chosen as a parent hydrocarbon. In this is the longest carbon chain. From this side, I will write the numbering: first carbon, second, third, and fourth. Now the name of this compound will be 1,3 butadiene. In this compound, we will start numbering. Suppose from this side, then this carbon is first, it is a second, third, fourth, fifth, and sixth. Now, if I started the numbering from this side, then this carbon has first numbers, here second, third, or fourth, fifth, and sixth one. So from both sides, we have given numbers 1, 2, 3, 4. Out of this, one numbering is correct and one is wrong one. And if we consider the numbering from this side, then this double bond has a second number, whereas from this side, this double bond has a first number. That's why numbering from this side is correct one, and accordingly we will give the name to this compound. Here at the 3 there is a presence of methyl, 5 there is a presence of methyl. Therefore, First of all, we will write here 3, 5 dimethyl. Then number of carbons are 6, therefore hexa, and the double bond they are present at first carbon and fourth carbon, therefore 1, 4 diene. In this way, we can name the alkadines according to the IUPAC nomenclature. Now, these alkadines, they are classified into three different types depending upon the position of double bond present in the compound. In 1,3-butadiene, the double bonds, they are separated by only one single bond. There is a presence of only one single bond. But in this compound, if you look the structure, the double bond, they are separated by two single bond. Therefore, the position of the double bond is different, and from the position of this double bond, they are divided into three types. And the first type is isolated diene, second type is conjugated diene, and third type is cumulated diene. So first type isolated diene. And the famous example is 1,4-pentadiene. CH2 double bond CH, CH2, CH double bond CH2. In isolated diene, we have to keep in mind two double bond, they are separated by more than one single bond. So here I will write more than one single bond is present between two double bonds. The second type is a conjugated diene. In conjugated diene, two double bonds they are separated by only one single bond. Therefore, here only one single bond is present between two double bonds, whereas in a cumulated diene, the double bonds they are in succession. CH2 double bond C double bond CH2. Therefore, in between two double bonds, there is a presence of a zero single bond. So from these three terms, you can easily understood if there is a presence of one single bond between two double bond, then it is a conjugated diene. If more than one single bond present, then isolated diene. If a zero single bond present between two double bond, then it is a cumulated diene. Out of the three types of dienes, in this lecture, we will discuss a conjugated diene, and name of that conjugated diene is butadiene. Which one? A butadiene. So I will write the structure of butadiene, that is CH2 double bond CH, a single bond CH double bond CH2, and the IUPAC name of this compound is 1,3-butadiene. It is one of the most important conjugated diene. It can be used in a number of chemical reaction, and it has number of applications. And that applications or chemical reactions method of formation we will discuss in the next lecture. In this lecture, we will discuss only the structural aspects of the butadiene. Now, to study the structural aspects of the butadiene, we have to compare this butadiene with isolated diene, that is 1,4-pentadiene. I will write the structure of 1,4-pentadiene here. CH2 double bond CH, CH2 single bond CH double bond CH2. Here it is a 1,4-pentadiene. I will put here only a pentadiene. Now look at the structure of butadiene as well as pentadiene. Number of carbons they are different, no doubt, but just see the number of double bond present in both compound. The number of double bonds they are equal to 2. How many double bond present? 2. Therefore, the one fact I am writing here, heat of hydrogenation. Heat of hydrogenation. Now, the number of double bond present in both compounds, they are same. That's why heat of hydrogenation in both compounds should be same. But it is observed that heat of hydrogenation in butadiene is less than a pentadiene. Is less than pentadiene. Why we are comparing these two compounds? Because the number of double bonds are same and heat of hydrogenation, but here a butadiene has less heat of hydrogenation than pentadiene by 3 calorie per mole. The second fact, which is different, in 1,3-butadiene, this double bond, it is having a carbon double bond carbon bond length. It is about 1.35 angstrom and single bond has bond length 1.46 angstrom, whereas in a pentadiene, this bond length is 1.33 and this bond length is 1.54. So it is clear that the normal values of bond length are carbon-carbon single bond length is 1.454 angstrom, whereas carbon double bond carbon bond length is 1.33 angstrom, and these values they are not observed in a butadiene, but instead of 1.54 we are getting 1.46 and 1.33, here we get 1.35. So the normal bond length values they are not observed in case of butadiene, though it possesses a double bond and a single bond in its structure. So these 2 points or these two facts, they are not explained on the basis of this structure. Therefore, to explain these two facts, we have to consider a modern aspects, and in the modern aspect or modern concepts, we will discuss resonance theory and molecular orbital theory. First of all, we will see resonance theory, and according to the resonance theory, how the bond length changes in the butadiene that we can explain easily. So let's begin with resonance theory. We know that if the compound possesses a double bond and they are in a conjugation, then the resonance occurs in that compound. I will write the structure of butadiene once again: CH2 double bond CH, single bond CH, double bond CH2. Whatever the conditions required for the resonance, they are present in the butadiene, and in this butadiene what happens, this double bond, when it is shifted to this and when it is shifted to this, we get a resonating structure like this. Here CH2 negative, then CH double bond CH, this terminal becomes positive. If this shifting is like this, then we get a different structure, and here we can write. Now, this carbon possesses negative charge and this carbon possesses positive charge. Along with this, we will write this type of structure also, in which terminal carbon possesses a single electron. In this way, we can write a number of resonating structures of the butadiene. These are the resonating structures. or we call it as a canonical structures of the butadiene just by shifting the double bonds, and we get a dipolar structures or diradical structures. And all these resonating structures, when they combine together, then we get a hybrid structures of the butadiene, and the hybrid structure that can be written like this. To write the hybrid structure, I will put here carbon, single bond carbon. This carbon is attached to CH2. It is attached to hydrogen and CH2. From this resonating structure, it is clear that the double bond, they are not fixed one. They are moving over the chain, and that's why we can write here, instead of writing a fixed double bond, we will write a dotted bonds here, and that indicates they are moving over the chain, carbon chain. In this way, we can write a hybrid structure of 1,3-butadiene. Now, at this carbon and carbon, there is a strong pi bonding, and in between these two carbon, there is a weak pi bonding. Now, as there is a strong pi bonding, the carbon double bond carbon bond length is somewhat increased, and it is about 1.35 angstrom. Here we know that we have written here carbon single bond carbon, but there is a weak pi bonding between these two carbon. That's why uh, the carbon single bond carbon bond length is somewhat decreased, and it is found to be 1.46 angstrom in this hybrid structure. In this way, this hybrid structure explains changes in the bond length. It is all about the changes in the bond length, how they are changing from normal values, and it is due to the resonating structure or hybrid structure of the butadiene. Then we will see why butadiene is more stable than pentadiene and why it shows less heat of hydrogenation than pentadiene by 3 calorie per mole. So the next point of discussion is molecular orbital theory. And in molecular orbital theory, the hybridization of carbon present in butadiene. Once again, I will write the example here. Butadiene has 4 carbon, and all the 4 carbons, they are in a sp2 hybridization state. Which hybridization state? Sp2 hybridization state. And due to the sp2 hybridization, it forms a 3 sp2 hybrid orbital and one unhybridized unhybridized p orbital. Now this 3 sp2 hybrid orbitals, they are involved in the sigma bond formation. Sigma bond formation. Suppose this is the carbon, it is a terminal carbon, then it will form a sigma bond with two hydrogen and one carbon. It is due to the sp2 hybrid orbital. This carbon also forms a sigma bond with two carbon and one hydrogen due to the sp2 hybrid orbital. But all these carbon, they possesses unhybridized p orbital, and due to this unhybridized p orbital, we observed a pi cloud above and below the carbon chain in the butadiene. Now let's see the pi bond formation in 1,3-butadiene. For this purpose, I have to write once again a CH2, CH, then CH2. It is a sigma bond formation. Then we know that unhybridized p orbitals are present on each carbon, and that unhybridized p orbital, they are parallel to one another. It means that on the successive carbon they remains parallel to each other but perpendicular to the plane. So I will write unhybridized p orbital on this carbon like this. Now these unhybridized p orbitals, they undergo overlap, and this overlap is sidewise. They overlap like this. These also overlap, and these also overlap. It is the pi bond formation in 1,3-butadiene. Here we know that CH2 double bond CH. In this way, pi bond formation take place. Now, if I number this carbon, this is the first carbon, this is second, this is third, and this is fourth carbon. Now, the carbon number second and carbon number third, the p orbitals present on these two carbon, they undergo a overlap, and that's why due to this overlap, the pi cloud which is generated covers all the four carbons, and this pi cloud is present above and below the plane of this 1,3-butadiene, and this pi cloud, it can be written like this: CH2 CH single bond CH, then CH2, and here the pi cloud is present above the plane, and here it is present below the plane. In this way, there is an overlap of p orbitals of carbon number second and carbon number third. That's why the pi cloud covers all the four carbons, and it present above the plane as well as below the plane. And due to this, the electron delocalization occurs all over the carbon chain, and due to the electron delocalization, the energy get decreased or it gets reduced, and that's why heat of hydrogenation is less as compared to the isolated dynes. And as heat of hydrogenation is less, the 1,3-butadiene is having a maximum stability than isolated dynes. So the main reason for the stability of 1,3-butadiene and heat of hydrogenation is a pi cloud present on above the plane and below the plane, and this pi cloud covers all the carbon chain or all the four carbons, and there is a electron delocalization occurs all over the carbon chain. So keep in mind, there is a electron delocalization, and that's why energy is decreased, heat of hydrogenation is decreased, and 1,3-butadiene obtain a maximum stability. In this way, we can explain heat of hydrogenation, stability of 1,3-butadiene, changes in the bond length with the support of molecular orbital theory and resonance theory. Now in this lecture, what we have learned that we are going to summarize in a few minutes. In this lecture, we have learned the meaning of alkadiene, that is a cyclic hydrocarbon having two double bonds. Depending upon the position of double bond, they are classified or divided into three types: isolated, conjugated, and cumulated. And the nomenclature is given according to the selection of longest carbon chain, and it is considered as a parent hydrocarbon. From the conjugated diene, we have studied a 1,3-butadiene. It is compared with the isolated diene, that is 1,4-pentadiene, and heat of hydrogenation and the bond length, they are compared with the 1,4-pentadiene or a normal value. Then it is found that heat of hydrogenation is less than that of the isolated diene by 3 kilocalorie per mole, though The 1,4-pentadiene and 1,3-butadiene possesses same number of double bonds. Here the bond lengths, they are different than the normal value. Normal values are carbon single bond carbon bond length is 1.44 angstrom, and the carbon double bond carbon is 1.33, but we get here 1.46 and here 1.35. Therefore they are different than the normal values, and these values they can be explained by resonance theory, in which we have learned the resonating structures and hybrid structure of 1,3-butadiene. The hybrid structure explains most of the properties of butadiene. In the last part, we have gone through a molecular orbital theory, and in molecular orbital theory we see a sp2 hybridization of carbon present in the 1,3-butadiene. sp2 hybrid orbitals are taking part in the sigma bond formation, whereas unhybridized p orbital, which are parallel to each other and perpendicular to the plane, they are forming a pi cloud above and below the plane, and that's why electron delocalization occurs all over the carbon, and that decreases energy, and that decreases heat of hydrogenation, and due to the decrease in heat of hydrogenation, 1,3-butadiene attains a maximum stability as compared to the 1,4-pentadiene. In this way, we have discussed all about the structural aspects of the 1,3-butadiene. In the next lecture, we will discuss methods of formation and uh, reactions of 1,3-butadiene. So till then, goodbye. Thank you. Thank you very much.